All right, lesson 14. This is it. This is the last unit lesson of Unit 6. Oh, yeah, there it is. Unit 6, coordinate geometry. And here's what we're doing today. Nothing new. This is combining everything we know about coordinates, slopes, geometric figures, and theorems. We're putting it all together into proof. What are we trying to prove? Well, we're trying to take a look at some of these figures. And this is a which one doesn't belong, but we're going to use it a little differently. We're going to use it to look at the slopes. Some of these figures, what are they? Letter A, what is it? We don't know. Let's figure it out. So let's take a look at the slopes. We look at slopes and say, well, that if you make a little cross hit here, you can actually make these 4 triangles. And you'll notice that they're all congruent. So the first one has a slope of rise over run of 2 here and 2. So it's got a slope of 1, positive 1. And then over here we got a slope of negative 1 and positive 1 and negative 1. What does that tell us? It tells us that these opposite sides here, so if I look at the opposite sides, that their slopes are the same. That tells me those are parallel lines. So that tells me that what I've got there is a parallelogram for sure. And then when I look at the inside of that, I take a look at really the adjacent side. So if I'm going to make a quick line drawing on this, I'm going to use red here for a moment. I look at these side lengths right here and here. Their slopes are opposite reciprocals. Remember, opposite reciprocals? What does that mean? That means I got perpendicular lines. That means I've got right angles. So this figure really is truly a square. So it's a parallelogram, yes, but it is really even better. It is a square. All right, so we've kind of proven that. If you look down at D over here, you can kind of see the same thing. Opposite slopes, except with the vertical lines, it's really hard because you see a slope of 0 and then a slope of undefined. So it's really a little trickier, but that one's so obvious, we're not going to worry about it. Let's go over to the right here and take a look at these slopes. We've got slopes here for DC of 2. And it's just slopes, by the way. They're just M values. And here I've got a slope of negative 2. And then I've got 2. And I've got negative 2. And once again, I see this whole reciprocal thing, but they're not reciprocals. They're just opposites. There's no flipping going on here. Remember, a flip would be from 2 over 1 to 1/2 and negative. That would be perpendicular, but that ain't happening. That's not going on here. All right? But you'll do notice if you look at the crosshairs, the diagonals of this figure, the diagonals are perpendicular. Those crosshairs, they cross those, kind of horizontal vertical lines. So, and then we start looking at the distances. These are all the same triangle. So really those hypotenuses, they're all the same value. They're all equal. Well, a 4-sided figure with perpendicular diagonals is something. It's called a rhombus. That's what defines a rhombus. So that's why when we said you want to be knowing your geometric shapes and their properties. Do they have to have right angles? Do they have to have perpendicular diagonals? Do they have to be parallel sides? So we're really looking at 3 so far. We look at parallelograms, squares, rhombus, and then over here we come down to the bottom left. Let me say, wait a minute, what's that? Let's look at the slope first. Slope of ZW, 1, positive. Over here, down the bottom, XY, that's also a slope of +1. So we know those are parallel lines. We can put the mark on there. And then over here, we can see the slope on YZ is what? 1, 2, 1, 2. So it's a slope of -1. -1. So those are also parallel. You may not know it, but 1 over 1 and -1 over 1 are opposite reciprocals. You don't see it because you flip the 1, so that doesn't show up. But that means those lines are perpendicular. That means we've got right angles. That means we have a rectangle. So that's what that is. That's what this section's all about. That's what this lesson's all about, is checking the slopes and also checking the distances. Now, one thing we didn't do right here, we didn't do a lot of distance checking. So let's go back. Let's turn the clock back a little bit because we got kind of messy with the slopes. Let's take a look at those distances. and how we get those distances. There's a variety of ways here. Depends on what you see. A lot of people, I'm going to go right up here if you follow this highlighted one here, they'll say that this distance right here is 2, and they would be actually incredibly wrong. Because it's a right triangle, you could say that has a side length of 2 and a side length of 2. So you could use Pythagorean theorem and say that distance is up here. That is the square root of 2 squared plus 2 squared, or the square root of 8. Now some of us would know that as 2 root 2. Now that is a special right triangle, folks. So you can actually use special rights. Do you remember the old x root 2? That works. So that is one way to get it. And then in that case, those are all 4 equal. So 2 root 2 is actually the side length there. It's really just the distance from point to point. But we're not, if there's right triangles, we don't use the distance formula. We don't have to. There's no point in it. Let's go over the rhombus. Hello, Mr. Rhombus. What are you doing today? Let's see if I can get a different highlighter color here. That's an odd color. Let's go with red. Why not? There's a good red for us. So let's come on over to Mr. Rhombus and take a look at his slope triangles. There they are. So we know the slope there was 2, but what about the side lengths? That's 1, that's 2. What's this? 1, 2. It's not 1, 2, root 3, because if you remember, that was the other 30, 60, 90. So let's use the actual distance formula on this one. Actually, let's use the Pythagorean theorem. 1 squared plus 2 squared. That's 4. That's 1. That's 5. So that's the square root of 5 right there. And those are all the same because the triangles are all congruent. So we're using a lot of geometric theorems. We don't have to prove every single little thing known to man, but that's the idea. All right, let's move on. Let's cut to the chase here. Here's a quadrilateral. It's got vertices 0, 0, 4, 3, 13, negative 9, and 9, negative 12. It's all about the slopes, and it's all about the distances. So if we want to find out what type of quadrilateral it is, we need to know the slopes. And we need to know the side lengths, or what we call distances. So we're using Pythagorean, we're using the distance formula, but we want to know the slopes and the distances. Do we need the graph? Not really. It's not necessary. I put it on here just to kind of give it a visual. So if you want to use it, I use Desmos for this. You can use it by drawing the figure, but you want to make sure you draw accurately. So when I draw it, does it look like a rectangle? Yeah, it does. Okay, well let's use that, but let's find the slopes. Let's do the opposite sides here. So let's go with 0, 0 and call that point A. Up here at 3 or 4, 3, let's call that B. Over here at 13, negative 9, let's call that C. And 9, negative 12, oops, sorry, got my C wrong there. C is actually down here. What did we say that was? Oh no, 13, negative 9, that was it, that was the C. Sorry, my bad. And D's over here at 9, negative 12 is down here. Let's check it. Now the easiest way to check slopes, folks, look carefully here. It's just to get your change in Y. Watch this, up on the top with the coordinates. You can't see what I'm about to do, but here I am. I'm doing it. 0 to 3. So that's A to B. That means that's a change in Y of 3. And then from 0 to 4, that's my change in X, fourths. So that slope right there is 3/4. And now I can go down here from D to C, and I can check that as well and say, well, that slope is, here's D. From negative 9 to negative 12 is a slope of negative 3. That's a change in Y at least. And then from 13 to 9 is a change of negative 4. That's 13 dropping 4 places. That's actually negative, negative. It becomes positive, positive. So that becomes a slope of 3/4. So those two sides are bingo, bingo, winner, winner, chicken dinner, parallel. And now if I check the other ones, I'm really doing the same thing. So this idea of how to check slope from coordinates, that's all it is just going from point to point and checking the change in Y and the change in X. That's what slope is, the change in Y over the change in X. It's always been that. It always will be. Forever and ever, amen. So let's go ahead and dig in here from B to C. There's my A, B, C, and D. So that would be 3 to negative 9. That drops by Wow, 12. Okay, so that's actually going down by 12. Down 3 to 0, and then another 9. And then from 4 to 13 is going up by 9. So that's a slope. If we reduce it now, we reduce that down to minus 4/3. Guess what? It looks a lot like the negative reciprocal of 3/4. So it looks like those are perpendicular. Now I can check the fourth one. In the interest of time here, I'm not going to check the fourth one. I'm going to say those are right angles. Those are perpendicular. They're right angles. I got 4 right angles. I do need the distances. If I want to check distances, I've got to check them. I can check them with the Pythagorean theorem. I can check them with a variety of means, but we know the slope, so we know that. Let's go ahead and just get back over here and say, you know what? Forget the coordinates for a moment. Let's just go all out distance formula. Let's just do it. Why not? We're here. So the distance between A and B is really the square root of, and this is the real distance formula. This is the real deal here. You remember, it's kind of x2 minus x1. It's the difference of the x's squared plus the differences of the y squared. So it's that change. That's what change in x and change of y. All right, then let's take the square root of that. Okay, let's fill in the blanks here. 0, 0. So that's my x and my y minus 4 and 3. And you'll notice that it doesn't matter whether I do which point. You can switch them as long as you get the x's with the x's and you get the y's with the y's. That's what matters most. And now I noticed that this is 4 squared, which is going to be 16. 3 squared, which is going to be 9. That means that's the square root of 25 all together now. That's a 3, 4, 5 triangle is what that is. All right? So that length is 5. And then let's check the other one. Let's get rid of this distance form. This we already know kind of what it is. Let's fill in the blanks on this thing. Let's just use this as it is. So let's go from B to C. So I'm going to frame it up. I'm going to go with B. My x-coordinate is 4. My y-coordinate is 3. C. My x-coordinate is 13. My y-coordinate is negative 9. 3 minus negative 9. Now remember, this is difference of. So the difference between. So 4 minus 13, that would be negative 9. All right, and we should square that thing, so that gives me 81. Over here, 3 minus negative 9. Don't forget to cross your T's there. Minus negatives plus positive. So 3 plus 9 is 12. Going to square that one, we're going to get 144. So 81 plus 144 is 225. And if you take the square root of that on a calculator, you're going to get 15. So you're going to do all 4 of those sides, check the distances. One side's 5, one side's 15. So you can find the perimeter, you can find the area, all that fun stuff. So as far as this lesson goes, I'm going to cut this one right here and say, I found all the slopes. I found out that there was some negative reciprocals, there were some perpendicular lines, there were some parallel lines. Okay, that was calculating. Now, we did actually draw this out, but we don't have to do this. Have some fun on Desmos if you want. If you have a lot of free time, go for it. And we found those side lengths using the distance formula. So we used the slopes and the distances, and we got 5 and 15. At that point, perimeter and area, perimeter, 15, 5 is 20, that's 40. And the area is 15 times 5, 75. And that's our area. All right, so the last part of it, the questions 2 and 3 are really not the work. Really, the heavy lifting happens. What type of quadrilateral is it? That's the reasoning. It's all that work. So show that work. Be ready on that one. All right, that's the idea. And then our last piece here, this was the thing we did in class, and we sent you home. You'll notice something here. If you look at these lines, and you really look carefully at their slopes, really look carefully at their slopes. This one's got a change in y of 1, 2, 3, 4. I'm just counting. And a change of x is 2. This one goes a change of y of 4. This one change of x 1, 2, 3, 4, 5, 6, 7, 8. So now I can see the slopes of these guys. This one is 4 over 2, which is 2. That's positive. And over here, this one's 4 over 8, which is 1/2. And it's negative. Opposite reciprocals, those are perpendicular, ladies and gentlemen. They meet at a 90-degree angle. What does that mean to us? It means that angle right there is 90 degrees. And believe it or not, wherever I put that point on this circle, that same thing's going to happen. And the reason why that's happening, this is a geometric theorem for later, but if I connect a diameter to a point on the circle, I'm getting what we call an inscribed angle. And all those angles will be the same, believe it or not. No matter how I draw it, it's always going to be 90-degree angles. The slopes will always be negative reciprocals. And there's some beautiful artwork for you. And that is the end of the lesson at 15 minutes long, because there's a lot of slopes to calculate and a lot of distances to calculate. All right, so when they say prove it, I put a grid on here for you. I know the book doesn't. So if it helps you to draw, by all means, draw it. This is just a sketch for us. So 0, 0, 1, 3, 0, 4, and negative 1, 1. Right there. It's tiny. It's tiny, but it looks like it is a parallelogram. It says prove it. Prove it. Well, what do we need to prove? We need to prove that the slopes of the opposite sides here, 1 and 2, are equal. We also need to prove that the other opposite pairs, I'm going to call this the slope of side 3 and the slope of side 4, are equal. And then we need to prove something altogether entirely different, that the two adjacent sides are perpendicular. So we need to prove that M1, let's see, that's going to be this guy over here. Give me a second to get myself some highlighter. We need to prove that that one right there is perpendicular to this one. So that would be 1 over M3. So it's just, and that's a negative. So negative 1 over M. So you're proving that this slope on the left over here is the opposite reciprocal of this one. So we're still proving, we're still doing the same thing. It's all about the slopes and the distances. And then I want to get the distances. I'm using Pythagorean theorem, so in the distance formula. So that's putting it all together. That's tying the whole unit up. It's wrapping it up. Check the book key. The answers to all those book key problems, they're in Google Classroom. But bottom line, you need to be able to calculate. You need to be able to calculate the slope of a line quickly from coordinates and from a graph. And we worked on that in this lesson. You just understand those properties of geometric figures. In other words, what makes a square a square? Equal side lengths, right angles. What makes a parallelogram a parallelogram? What makes a rectangle a rectangle? And the good old rhombus. So we got to understand that stuff still. And then we need to understand that this connection between parallel, equal slopes, and perpendicular lines. Opposite reciprocal. Bottom line, then we just use them in theorems. So then we're using them to really prove geometric theorems. Yeah, look at that. Oh, that's the end. So sad. No, it's not. It's Friday. I got to get out of here. So, I don't know. See y'all? Yeah, why not? See y'all next time. Later. Oops, that's a bad later.